Today we will continue our discussion about logarithmic functions. We need to be certain we understand clearly that a logarithm is simply a different equation form we can use in order to solve for an exponent. So we need to begin with the section that actually defines this for us. I've had to write in a correction. My document did not upload correctly. Yours that you're looking at should have the correct symbols written there, where it's x equals a to the y power. That is equivalent to y equals log base a of x. Now, here's the form that you need to understand so you can work from either form. There are times you need to change an exponential equation into logarithmic and vice versa. And what I want you to observe is this, that the base, when it is in exponent form, will still be the same base you see when it's in log form. And in log form, it is written as a subscript, a small number just to the right, and a little below where you see the word log. Now the exponent that we have in exponential form becomes the answer when it is in log form, because remember, a log is simply a tool for solving for an exponent. That would mean the answer when it is in exponential form becomes what we call the argument in log form. That is the value that follows the base when it is in log form. So the expression log base a of x simply represents the exponent to which the base a must be raised in order to obtain x. Now let's go to a table that we have where we're going to practice going from one form into the other. So let's make sure you get very comfortable doing this. It is essential that you are proficient in this skill in order to be successful in this chapter. So if I'm looking at 3 to the 4th power equals 81, and I want to turn it into log form, that would mean log base, well, my base is 3, of 81 equals, what was my exponent? Well, that value was 4. Now the next one, you can see I had to write in a negative in front of the 3. For some reason it didn't upload either, but you're looking at log base 1/2 of 8 equals a negative 3. So to go back to exponential form, my base is 1/2 raised to the power of negative 3. That value should equal my answer of 8. Notice the positioning. Bases are still the same. The answer in the log form becomes the exponent in exponential form. The argument in log form becomes the answer in exponential form. Now, if we look at 10 to the 3rd power equals 1,000, we need to remember when we are going into log form, the log form of a log is the common log. That means it's understood to be base 10 unless I have written in a different value for the base. So when I check this in exponential form and I see the base is 10, it means it's optional, whether I put it down there or not. I'm not going to because it's understood to be 10. If you wanted to write it in, that's fine. 1,000 is now the argument when it goes into log form, and the answer of that would be my exponent 3. Okay, one more. Let's go from log base 5 of 1 over 125 equals negative 3. Put it into exponential form. My base is 5. My exponent is negative 3. And that is equal to the fraction 1 over 125. Now pay close attention to these next two examples, because if you can remember the patterns, it will save you some time. It's very useful to know these. I have 12 to the 1st power equals 12. So if I go to log form, my base is 12, but so is my argument. Now, that is like saying 12 raised to what power gives you 12 for an answer? Well, it has to be this exponent value of 1. And that's an important pattern you want to identify. If the base in log form matches the argument that follows it, if they are identical, your answer will always be 1. It has to be an exponent value of 1. Now the last one, if I take that into exponential form, my base is 6, but what's my exponent? It's 0. Well, what is anything raised to the 0 power going to equal? It equals 1. Therefore, if I see the argument is 1, it will always mean that the exponent had to be 0. It will give me a value of 0 in log form. Okay, those are important to know. Now let's practice solving a few logarithmic equations. Now, when I see that I have an equation and it has a logarithm in it, I don't really think in logarithms. I haven't spent a lot of time working with them. I doubt you have either. But I'm a little more familiar with exponents. So the first strategy we're going to take is turn this back into exponential form. So I'm going to start by rewriting this as my base is x raised to the negative 2 power, because that's where my exponent should be, is equal to 16 over 9. Now, a couple of things probably bother you. First, you're seeing a fraction, but you're also seeing a negative exponent. And ultimately, remember, where you're trying to go is you want to know what x would equal. So we have several different paths we could follow to solve this, but I think the most direct one is probably just thinking about what can I do to get rid of that exponent of negative 2 so it just becomes x to the first power. And if you think about it for a moment, as long as I raise a power to a power, that means I multiply exponents. What would I multiply negative 2 by to turn it into a positive 1? Well, I multiply by the reciprocal. So if there happens to be an exponent on my variable that I'm solving for, I can remove it or eliminate it if I raise each side to that reciprocal power. So when I take negative 2 over 1 and I flip it, I get a negative 1/2. But following the rules of algebra, if I'm going to raise one side of an equation to a power, I have to raise the other side to the same power. So I'm going to raise both sides to a negative 1/2 power. That means on the left, I just get x. On the right, now I have 16 over 9 to the negative 1/2 power. So not only do I have a fraction, but now I have a negative exponent that has a fraction as well. So let's start cleaning this part up. The first thing I want to do is get rid of the negative exponent. Remember, all it tells me about is location. So that means whatever's in the top of my fraction needs to go to the bottom, and whatever's in the bottom needs to go to the top. So let's flip the fraction, and that will mean we now have 9 over 16 raised to the positive 1/2 power. The next thing that will help me simplify this is remembering that fractional exponents can be rewritten in radical form. All I have to do is take the root of whatever is the denominator of the fraction. In this case, because it's a 2, that tells me I'm taking a square root. And x would equal the square root of 9 over 16. Well, the square root of 9 is 3, the square root of 16 is 4. That's going to clean up to be x equals 3 over 4. Now technically, let me mention, because we inserted the radical into the problem when we raised both sides to the negative 1/2 power, it means we do need to consider the fact there are two roots, a positive and a negative. So not only would positive 3/4 be a solution, we need to consider negative 3/4. Here's the dilemma. If I look at the original problem, my base is where the x was, and I am restricted by my domain to have values that are greater than 0. Therefore, I don't have to consider the negative 3/4, and x equals positive 3/4 will be my solution. Lots to keep up with in there, but by taking it into exponent form, it should be solvable. Look at your next example. Log base 16 of x equals 3/4. Well, if I go into exponential form, I'm going to get 16 raised to the 3/4 power equals x. Now you might be tempted to want to raise each side to the reciprocal power, but notice x is already by itself. I don't want to put some exponent on x because I'm trying to find out what x is equal to as it is. I just need to clean up or rewrite what 16 to the 3/4 power is. Remember what we said about fractional exponents? They can be rewritten in radical form. But in this case, it's not a square root. Since my denominator is 4, I'm taking the 4th root of 16. My numerator in this fractional exponent is a 3, so that means I would then have to raise that answer to the 3rd power because the numerator remains as an exponent. Now to clean up the 4th root of 16, if you do not know what number you multiply together 4 times and the answer is 16, that's where you go back to your prime factorization. 2 would go into 16 8 times. 2 goes into 8 4 times, and 2 goes into 4 2 times. Look at that. We have 4 of these 2's being multiplied together. So the 4th root of 16 is 2 raised to the 3rd power. That means x equals 8. 2 down, 1 to go. Look at this last example. If I pull it back into exponential form, I have 36 to the, what would be my exponent, x power, equals the square root of 6. Okay, this time the variable is the exponent, so that's not going to help us very much as far as being able to do something to eliminate the exponent, but this is where I apply the strategy we talked about earlier. If we could get the bases on each side to be the same, that might work out for us in coming up with something we could solve. The problem I have is on the right side there is a radical. So I need to rewrite that with a fractional exponent so I can have a base of 6 and it's raised to the 1/2 power. And I know it's raised to the 1/2 power because it was a square root and that was an index of 2. Now, if I look at this, I have 6 as one of the bases, 36 as the other base. I can rewrite 36 as 6 raised to the 2nd power. If I do that, I now get this equation. My bases match. That means, because I have a power raised to a power on the left, I multiply those exponents. I get 2x equals the exponent of 1/2 on the right. Now I can either divide both sides by 2 or multiply by the reciprocal, which is 1/2. Either way I go, I'm going to come up with x equals 1/4. And that would be some examples of how you would solve logarithmic equations. Now, within working with these log equations, there are times that we may need to even rewrite what we see in a little cleaner form. And to do that, we need to know some properties or some rules of working with logarithms, very similar to the rules we reviewed on exponents as we began this chapter. In fact, because exponential form can be written to be equivalent to logarithmic form, all the rules that apply for exponents are also going to apply for logs. The challenge becomes, because the forms look different, do we recognize what those rules are going to look like? So let's run through a few examples here to make sure these properties would make sense to you. The first one is the product property. Now, before we actually read what it says about logs, let me illustrate what that looked like in exponential form. It meant if we had x to the 3rd times x to the 4th, that would equal what? X to the 7th, because what did we have to do? If we were multiplying and bases were the same, that meant we would add exponents. Now, look at your rule when it's with logarithms. Remember, logarithms are the exponents. So if the exponents, when it's in log form, these arguments are being multiplied together, it can be pulled apart as the sum of the logarithm of the numbers. So it's the same rule, it just looks a little different in log form. If we see a product after the log, if the argument is a product of numbers, separate it out with plus signs, just like we would have added if we were multiplying and bases were the same. Now, when it's the quotient property, think about this. If I had x to the 5th power and I were to divide that by x to the 2nd power, that would equal x to the 5 minus 2, which is x to the 3rd power. In other words, if we were dividing and we saw that we had the same base, all we would have to do is subtract the exponents. Now, look at your quotient property. If you have a fraction or a division problem in the argument in a logarithm, that would tell us that we could separate them into logs and take the difference. We would subtract them. Same rule, it just is in a little different form because they are logarithms. The next one you may have to think just a little harder. And if I were to remind you of this power rule that we have, if we had x squared and we raised it to the third power, what did we say that we would do with those exponents? Well, we said we would multiply, and 2 times 3 is 6. So we're multiplying the exponents together. Now, think about this for a minute when we're talking about the power property with logs. If you see an exponent on your argument when you have something in log form, here's what you need to keep in mind. The log expression all by itself is an exponent, right? So it is a power being raised to a power, therefore that means we multiply them together. When we multiply, it means pull down that exponent that's on the argument, bring it in front of the log, and multiply together. So we would simply take the exponent multiplied by the logarithm of the number. Now these last two rules, we're kind of reviewing some things we discussed earlier. We have log base A of 1. Remember what I said before? If your argument is 1, the answer will always be 0. As long as the argument was 1, the only exponent that would give me a value of 1 is an exponent of 0. And if our bases match up, the base on the log with the argument that follows, if those are identical, then that would mean that we have to have a value of 1 when we evaluate that logarithm. The exponent, the only one that would work to give us that same value back, would be an exponent of 1. Now, using these log properties, we are going to do some expanding, and you will want to make this correction on your paper. There was a little formatting issue on what you would have where it has a box between the 8 and the 6. It really should be a dot. So we have the product of 8 times 6 we're taking the log of. If I go back and I look at those rules, that product rule tells me that it would become log base 7 of 8. And because I was multiplying, I'm going to separate these with plus signs. So log base 7, 8 plus log base 7, 6. And that uses that product rule for logarithms. Now, if you look at the next one, it's a division problem. It's a quotient. Remember, if we're going to separate these back out, what do we separate them with? We're going to use a subtraction sign. So it becomes log base 6 of what's in the top of the argument, which is 12, minus log base 6 of 5. And that's all we're doing. We're just simply, this is called expanding our logarithms. We're going to write them as a sum or a product of terms. So we're stretching them out. We're expanding them. Now, if you look at C, here's something you need to be careful about. I see a radical, and we didn't have any rules for working with radicals, either for our exponents or for our logarithms. But I can rewrite those radicals as fractional exponents, and that would be step 1. If this is rewritten as log base 2 of 9 to the 1/3 power, now I see a rule I can use, because if I have an exponent on the argument, remember that power rule tells me I can pull it down in front and multiply it times the logarithm. So it would become 1/3 times log base 2 of 9. That's all you do, is take the exponent, pull it down in front, and then you would multiply. Okay, D gives us a lot to work with, and I'm going to make this suggestion because we have all of our rules rolled into this same problem. When you see you have a fraction involved and there's more than one term, probably the simplest way to begin pulling this apart and separating the terms is anything that's being multiplied together in the numerator of the fraction gets separated with plus signs. Anything that's in the denominator is going to get separated by a minus sign. So we're going to begin by writing this as log base b of r. I'm still in the numerator, so I need a plus log base b of s squared plus log base b of t. Now, I'm through with the numerator. As I move to the denominator, remember it needs to be separated by minus signs, because on the quotient rule, it tells me if I'm going to have something that was divided, I have to make it a difference of the two. So I'm going to have to subtract what's in the denominator, and that becomes log base b of u to the third minus log base b of v to the fifth. Wow, that's a lot of terms. There's only one thing left to do. I look now and I have a few terms that have exponents on them. I simply need to pull these down to the front and get rid of the exponent. So that's going to be log base b of r plus 2 log base b of s plus log base b of t minus, let's pull down this 3, and it becomes minus 3 log base b of u minus 5 log base b of v. And that would be our cleaned up expansion of those logarithms. One more example, and this one again has a radical. So what we want to do is rewrite it as a fractional exponent. Now it's r to the third, and then we're taking the fifth root of it. There's a couple of different ways you could think about it, but remember we said the fraction exponent means the denominator is the root, and then any other exponents would be in the numerator. So I could actually go straight to a fractional exponent with this if I understand that 5 has to be in the denominator because it's the root, and then I see an exponent of 3 on the r, that goes to the numerator. This is log base a of r raised to the 3/5 power. Now I can use that power rule, and when I pull down that fraction exponent, I get 3/5 log base a of r. Okay, look at the last one. If we do the same thing we just discussed, we're going to rewrite each of these terms with fractional exponents. Notice what the denominator in the fraction should be, though. Our root is m. It's not a number, it's a variable. That's okay. We'll just make it log base a of r to the 3 over m power. Now I'm still working in the numerator, so before I get to the next term, I need to put a plus log base a of s to the 2 over m power. Now I'm ready to move to the denominator. So before I write this term down, I need to put a minus sign. And I would have log base a of t to the 4 over m power. And now that I've done that, I just simply need to pull those exponents down in front of the logarithms. And that will give me 3 over m log base a of r plus 2 over m log base a of s minus 4 over m log base a of t. So make sure you would know how to expand these correctly. Well, guess what? We also can go the other direction and we can condense, or we can write something that's separated as individual terms back as a single log expression. So we're going to work backwards. If I see a minus sign, that's going to tell me there's a fraction. If I see a plus sign, that's going to tell me things are multiplied. If I see both of them, that's going to tell me things that come after the plus sign go in the numerator, things that come after the minus sign go in the denominator. And if I happen to see any values in front of the word log, that tells me it's going to pull back up and become an exponent. So let's see if we can put all this together and rewrite these as a single log expression. Now, very carefully, make sure it's log base 4, and I have to be sure every one of these terms has the same base. They do, and I would not expect anything tricky like that in your homework or on the test, but you need to realize the reason we can condense this is because they all had the same base. So this becomes log base 4 of x that's going to be in my numerator because it's positive. There wasn't a minus sign in front of it. But then I see a minus sign. What follows log base 4 with that minus sign? It's a y. And that tells me I need a y to go in the denominator. Anything that had a plus sign in front goes on top. Anything that had a minus sign goes on the bottom. Now, where does the z belong? That third term, since what's in front of the log term that has the z as the argument is a plus sign, that tells me to put the z in the numerator. And that's all there is to it. Let's look at the next example. Now, if you noticed when we were expanding, we would pull down exponents the very last thing. Now that we're going to be condensing, if I see there are values in front of the log, I'm going to want to put them back up as exponents in the beginning. So this becomes log base b of r to the 4th minus log base b of s to the 5th. Now that I have these two terms written and I see I have a minus sign, tells me I'm going to have a fraction, I'm ready to write my single log expression. It's going to be log base b of what's on top is the r to the 4th. After the minus sign is where I see the s to the 5th. That goes on the bottom. That's all there is to it. Okay, now we have one that has some fractions. We will need to pull those up as exponents. Also, we have a little formatting issue on your screen here. This needs to have a minus sign in front of the log base a of xy. So if I get ready to pull these things up, I see I have log base a of x to the 1/3 power plus log base a of y to the 2/3 power, and then there's a minus log base a xy. So I can already tell I have a fraction, but I also have these fraction exponents. And when I clean this up to a single log, if I notice that these fractional exponents have the same denominator, this is actually going to clean up to look a little bit neater if I rewrite these in radical form. So right now I'm just going to, with the plus sign, that means the x to the 1/3 and the y to the 2/3 goes in the numerator. I'm going to have an xy in the denominator, but when I go back into radical form from the fraction exponent form, since both of these denominators in the fractional exponents are 3's, I'm going to take the cubed root of x to the 1st power, y to the 2nd power over my xy on the bottom. And that would be condensed in simplest form. So the remaining example we have for theorem on inverses gives us an explanation of one property we've already discussed, but another one that you probably haven't seen but is easy to understand. If you were to change this first property, a raised to the log base a of x power equals x, into log form, look at what you would have. You would have log base a of x equals your exponent, which is log base a of x. Obviously, that is true. So that would explain if your base matches the base in the logarithm when it's an exponent, whatever the argument is will actually be the answer, what it simplifies to. The second property says log base a of a to the x is equal to x. Likewise, if you were to take this and put it into exponential form, you would see why this property holds. If you were to take base a, raise it to the x power, that would be equal to the argument a to the x. Obviously, that's true. Recall that we saw earlier, if the base on the logarithm matches the argument, the answer becomes the exponent. Now, as we move into this next section, it's a reminder that logarithms, log logarithms, are common logarithms, and they will automatically be understood to be base 10 unless you had a different base that was noted. In this case, we do not have a base that is noted. So log x is the same thing as log base 10 of x. Therefore, we understand the base to be 10 if we don't see one. Now, some of the questions you would be asked to answer on your exam would be to make sure you can input these into your calculator accurately. So experiment with your scientific or your graphing calculator to be sure you have the order of entry correct. If you were to take the LOG, common log of 10,000, the answer would be 4. If you were to find the log of 341, notice that's asking 10 raised to what power would give you 341. Obviously, this has to be a fractional exponent. In a case like that, on the test, it will tell you what to round your answer to. For our example in notes, I will tell you round to the nearest thousandth. Be sure that when you put it in your calculator, you would end up with 2.533. The last example would be 10 raised to what power gives you 0.06894. Make sure that you're getting negative 1.162 in your calculator. Now, the last thing is just a reminder. If you look at that last one, you may be a little puzzled. Why did that end up being a negative value? Well, it's simply because if we were going to take base A logarithms of numbers between 0 and 1, so something that's less than 1, remember our base has to be greater than 1 to fit our domain restriction, then you will always get a value that's negative, because the exponent would have to be negative in order to give you back something that would be very close to that asymptote that follows the x-axis, just as we saw in the graph in section 4.1. Now, this is a reminder, when you see natural log, it's understood to be base e. If you wanted to write the natural log of x using the common log notation, you can. You just have to make sure that you write in base e as the base when you do so. So again, let's check to be sure calculator entry is good. In fact, you don't even need the calculator on the first example, because the natural log of e to the fourth is asking e raised to what power would give you e to the fourth. Obviously, the answer is 4. If you type in the natural log of 341, make sure you are finding 5.832 as your answer in the calculator. And the natural log of 0.06894 should give you a value of negative 2.675 when you round to the nearest thousandth. Okay, last thing we will cover and then we'll be done. If we want to evaluate logarithms that have a base other than 10, there actually is a way you can do that in the calculator. You can, as long as you use what's called the change of base theorem. Here's how that will work. If I ask you to evaluate log base 4 of 20, the problem is, if you were to take it back into exponential form, this is asking 4 raised to what power would equal 20. Well, obviously, I can't get a common base between 4 and 20 and use the rules that we were using before in order to solve for it. It's got to be a decimal value for the exponent. I know 4 to the second power is 16, but when I go to 4 to the third power, that's 64. 20 is in between those numbers, so it's got to be 2 point something. The calculator can actually find it for you if you convert these to base 10 logarithms and you divide the log of the argument divided by the log of the base. So if you were to type in log 20 divided by log 4 in your calculator, make sure you carefully enter it, you close off parentheses where you need to, you would come up with a value. And this tells us to round to 4 decimal places here. You should get 2.1610. Now that 0 is necessary because the instructions said round to the nearest thousandth. That means we need, or round to, not to the nearest thousandth, the nearest 10,000th. There are 4 places to the right of the decimal. That means that if we don't include the 0 and we put 2.161, it appears that the answer was exactly 2.161. The 0 indicates we did round to get this answer. If you were entering the example B in your calculator, you would want log of 0.7 divided by log of 2. And if you type that in your calculator, you should get a value of negative 0.5146. Make sure you know how to use your calculator correctly.